Alright, welcome back everyone. This video we're going to be talking about functions between sets. So the idea of a function is an object that uh, tells us how to associate elements of different sets to each other in some sort of hopefully meaningful way. So the most ubiquitous example in physics is that of a function of time. So this function could be telling us what is the position of a certain particle or object based on what time it is. Or maybe given what time it is, we can say what the velocity of the particle is, or the kinetic energy or potential energy, or so on. There's so many things that can be given as a function of time in physics. And in other contexts, sometimes it's useful to interpret a function as serving as a sort of identification between different spaces, or as different sets in general. So previously we saw this example of making this identification between the complex numbers and R2 is a sort of way to translate between two different perspectives in a sense. So these are sort of two different spaces, but in a way we can kind of think of them as the same. And the actual mathematical way of thinking of them as the same set is through this function that served as our identification. So it just depends on the context, and since some situations will lean towards the interpretation of the identification. So we'll see that when we work with groups and linear algebra, where we work with vector spaces. And then when we do more physics-y stuff, we'll take this interpretation of this sort of association or sometimes transformations. Okay, but regardless, a function from a set a to b. So this is how we're going to write functions now. You're probably used to this whole y equals f of x thing, and we'll do a little bit of that or something that looks like that, but for the most part, this is how we're going to express our functions. So this is our function f, and this is telling us it maps elements of a to elements of b. So this f from a to b is an object that maps elements of A to elements of B. And sometimes the word map is used instead of function. They just mean the exact same thing. Map is kind of used because the idea is that we're given an element of A, this function, this map, tells us where to go to in B. So f will take, let's call this little a is an element of A, to an element of B, a specific element of B, that we'll call f of A. And this is a bit more similar to the y equals f of x form that you're familiar with. Oh, forgot an s here. And so a way that we can kind of envision what's going on is if we, say, draw out this set A, and mainly we're just going to focus on finite sets. So even though I've drawn this region, really I'm going to think about A as just this finite set of points. And then here we'll have B, which has this set of points. And now when I say that I'm mapping from A to B, that means if I look at an element of A, there's some association with an element of B that's specified by this function f. So overall, I have this map f from A to B, and this specific element of A might be associated to this element of B. All right, so I draw these lines to make these associations. that happen through the function f. So a goes to f of a. And then maybe this one goes here. And this one goes here. And now there are certain rules that we have with functions. So kind of the first rule is that each element of A maps to an element of B. Oh, sorry, that's supposed to be capital. Each element of A, the set A, maps to an element of B. So we can't have some point in A that just doesn't get mapped to anything. That's not allowed. Then it's not truly a function from A. And the second rule is that no element of A maps to multiple elements of B. Okay, so you could sort of combine these two rules together to say that every element of A maps to exactly one element of B. But there is actually a reason that we separate these two rules out, and we'll see that probably in the next video. Okay, together, these two rules form what we call well-definedness. So well-definedness of a function. That's a bit redundant because we're saying that functions need to be well-defined, but that's language. And the second rule you should actually be pretty familiar with because it's what you learned as the vertical line test. So if you think of these functions as functions from the reals to probably the reals again, so you're thinking about functions from real numbers to real numbers, you had this vertical line test where if you had a vertical line in the graph and it intersected, here, let me draw this out. If it intersected 2 points, then you said, no, this is not a function. And what's the reason? Well, if you think about this input being your A, and then the y-coordinate of these points on the graph are telling you the values of the function. Well, if you intersect twice, or if it's a vertical line, then you're saying you're at the same input A. Right? If you intersect twice, that's telling you have two different values. Well, that's a problem because we're saying no element of the input space maps to multiple elements of the output space. But in the vertical line test, if you intersect multiple points, that's exactly what's happening. So that's why we would say that a graph like this does not correspond to a function. Okay, a few definitions. If we have a function f from a to b, so definitions. A is the domain of f, and B is the range of f. So these are probably things you should have heard of. Sometimes the range is also called the codomain. Usually in America it's called the range, but I know here in England it's called the codomain usually. Yeah, I had an English lecturer, or not English, an English lecturer at UC, who would also call it the codomain pretty frequently. Yeah, so when I was saying earlier, this input space and output space, What I really mean is the domain and range of f. All right. So we can define a few more things. One is an argument, or let me say arguments and values. So an argument is the input of a function. So you could sort of describe this as an element of the domain. And usually we'll use the term argument in generality, so we'll say that if we have a function like f of x that you're used to, then we say that the argument of the function f is x in this case. Or if we have multiple things that we input into the function, like let's say we have something that depends on both position and time, and we have f of xt, well then we say that f has multiple arguments, which would be x and t. Okay, and then the value of given a specific argument, a specific input, is an output of the function. So e.g., when we had b equals f of a, right? When we were first introducing our idea of a function, this b is the value of f at a. Okay. So let's talk a little bit about functions before I introduce some more definitions. So we saw one example where a had less elements than b, right? I'm just gonna move this actually. So a has 3 elements, b has 4 elements. And you might have noticed that in our earlier example, there was one element of b that was not mapped to, right? If you think about it from a accounting perspective, you can make a very simple natural argument that there's no way that we can map to all the elements of b just from a without violating this well-definedness of the function. And particularly, we would have to violate our sort of analog of the vertical line test, right? When it does violate this, so this mapping to multiple elements, that's called multi-valuedness, or multi-valued. And when it just maps to one, like we want it to be, we call it single-valued. Right. So there's no way to get to all of the elements of b without having the function be multi-valued at some point. So we would probably, we could do something like this, but now we see that, if this is a, we map to 2 different elements of b, which is, not good. So if the size of b is greater than the size of a, then we have that not all of b is mapped to. Okay. Now, maybe let's consider a situation where a has more elements than b. Well, now it's pretty easy to map to all of B, right? Now we can just go here, here, here. And now this last one just has to be forced into one of the elements of B that they all have already been mapped to. Okay. So maybe you want to say, well, if the size of A is greater than the size of B, then B must be mapped to entirely. But that's not true, because we can construct a pretty easy example where all of the elements of A just get mapped to the exact same element of B. They all just converge to this one point. So it's not true that B must now be entirely mapped to. But what is true, for the same reason as our previous example, is that we can never have distinct elements of A mapping to distinct elements of B. Right, so we do not have distinct elements of A mapping to distinct elements of B. Because if we did, then there would have to be at least 4 elements of B, right? Because we have 4 distinct elements of A. If we map to distinct elements of B, then we need to have 4 elements of B that are mapped to, but there are less than 4 elements of B. So it just can't happen. So this is when the size of A is greater than the size of B. Okay. And now, if they're equal in size, now it's possible to get this sort of one-to-one correspondence that's, between the entire sets. So here we have each element of A maps to an element of B. It maps to the whole set B, and distinct elements of A map to distinct elements of B. Right, so we might call this one-to-one. And actually, let me just write out 1-to-1. And let's call it entire. We're going to use a different term later on. We're going to define one, but for now let's call it entire. So the idea that it maps to the entirety of B. And the one-to-one is basically saying that distinct elements of A map to distinct elements of B. Okay. Or we can also call this onto, because it's mapping onto the whole of B. So this is when the size of A is equal to the size of B. So, right, so this maps through F. This doesn't have to be true, right? The fact that this function in particular is one-to-one and onto. But all that we're saying is that it could be true. And it's only possible when the two sets are of equal size. Right, we could have this sort of degenerate example where all the elements of A map to the same element of B. Right? But all we're saying is that this sort of nice situation is possible, and it's only possible when they have equal size. Okay, so let me introduce some more definitions. So this is the definition of the image. So if we have a function from A to B, the image of f, which we denote as imf, conceptually, it's the set of values of f, which specifically is saying that it's the set of f of a such that a is in the set A. Okay? This might be a little weird to read at first, but I think you come to get used to it. So as long as a is in the set A, this is giving you a value of the function. And considering all the possible elements of a will give you all the possible values of the function f. That whole set gives you what's called the image. So if we look at some of our examples, in our first case, our image of the function is these 3 points, because these are the points that are mapped to. There are values of the function. In our second case, it's just this 1 point. In our last case, one of our special cases, the image is the entirety of B. Okay? Now I want to emphasize that this is an abstract idea of what a function is. You're very used to this idea of like functions being graphs, right? And it's all about, y equals f of x, and you have these curves in a graph, and they correspond to these like real numbers, right? But functions are not really about that. They're about associations between sets, and sets can have any degree of abstraction. So we need to sort of open our mind and allow this generalization to exist comfortably within us. This more general idea does not have to relate to numbers. Okay. Since I'm already going, I'll give you the next few ideas. So if our function maps distinct elements of A to distinct elements of B, that's an important concept, right? Because in some sense, that's kind of preserving the information about where the elements came from, right? So if there's some information associated with the elements of A, right? And then we have some function that goes into B. If the function maps distinct elements of A to distinct elements of B, then we can trace it back and identify where we came from through the function. And so if there's information about the elements of A, that then gives us information about the elements of B, and that information is preserved. So if we can go this way, and our function has this property, we can also go back from our values of the function. Okay? So saying that our function maps distinct elements to distinct elements is saying that if f of x equals f of y, right? So we have two elements, x and y, that map to the same thing through f. This is only possible if x is equal to y. It's not possible when x is not equal to y. Okay? This concept is called injectivity. it's also called one-to-one, as I was saying before. These are completely equivalent. And our other idea, which was when the function was onto, when it mapped to the entirety of the range. So another way of saying that is that the image of the function f is equal to the range, right? So the image is the set of the values of f. If it's equal to the range, that means that every element of the range is a value of the function. Okay, this is called surjectivity. Or onto. Let me be consistent. If we have both together, this is called bijectivity. Okay, and then if we're using the noun form, for a function, we would have an injection or a surjection, and then together would be a bijection. Okay, so this is a bit mysterious so far, but in the next video we'll talk about why these concepts of injectivity, surjectivity, and bijectivity are actually hugely important. And the other thing we'll do is make a connection to this idea of graphs that you're very familiar with, and that's probably how you mainly think about functions. And we'll also tie that in with Cartesian products, actually. So stay tuned for that, and I'll see you in the next one.